For centuries, we have looked to the skies to predict the weather or guide our ships. But today, the atmosphere serves a more industrial purpose. As the global demand for energy rises and the need to decarbonize our atmosphere becomes urgent, wind power has emerged as a cornerstone of the renewable energy revolution. It is a technology that bridges the gap between ancient mechanical wisdom and cutting-edge material science, transforming the invisible kinetic energy of moving air into the electrical lifeblood of our modern cities. The concept isn't new. As early as the 7th century, the Persians were using vertical axis windmills made of reeds to grind grain and pump water. By the Middle Ages, the iconic horizontal axis Dutch mill appeared in Europe. These weren't generating electricity, of course. They were performing mechanical work. The wind's kinetic energy was transferred through wooden gears to heavy grindstones. Everything changed in 1887. In Cleveland, Ohio, Charles Brush built the first automated wind turbine for electricity production. It was a behemoth, a 12-ton monster with 144 cedar blades. While it only produced 12 kilowatts, it proved a fundamental concept. We could turn the movement of air into a flow of electrons. To understand a modern turbine, we have to look at aerodynamics. Most modern turbines use a 3-blade design. Why 3? It's the Goldilocks number. Stable enough to avoid the wobble of 2 blades, but lighter and more efficient than 4. The blades aren't flat planks. They are aerofoils, shaped exactly like aeroplane wings. As wind flows over the curved surface, it creates a pressure difference. This generates lift, which forces the rotor to turn. Once that rotor spins, the magic happens inside the nacelle, the head of the turbine. The low-speed shaft. Connected to the blades, it spins at a modest 10 to 20 revolutions per minute. The gearbox. This is the heart of the mechanical system. It uses a high ratio to step up that slow rotation to over 1,500 RPM, fast enough for the generator. The generator. Using electromagnetic induction, copper coils spin within a magnetic field, forcing electrons to flow and creating an alternating current. This process follows Faraday's law. As the magnetic flux through the coil changes, a potential difference is induced. This energy transfer relies on the kinetic energy of the wind being converted into electrical energy, though some energy is always dissipated as heat due to friction in the bearings and electrical resistance in the wires. But the wind isn't always consistent. That's why turbines use pitch control. Small motors in the hub rotate the blades themselves to catch more wind or feather them to stop the turbine if the wind becomes dangerously strong. This allows the turbine to maintain a constant power output despite variations in wind speed, ensuring the frequency of the electricity remains stable before it enters the national grid. Despite their efficiency, wind farms often face local opposition. Critics frequently cite visual pollution, arguing that these towering structures mar the natural beauty of the landscape. There are also ecological concerns, particularly regarding the impact on local wildlife. If not carefully sited, turbine blades can pose a risk to migrating birds and bats. Furthermore, the construction of offshore foundations can temporarily disrupt marine ecosystems through noise and seabed disturbance. In terms of energy density, wind power operates on a different scale than fossil fuels or nuclear energy. A single large coal or nuclear power station can produce upwards of 1,000 megawatts of continuous baseload power. In contrast, a single modern onshore wind turbine usually produces between 2 and 5 megawatts. This means thousands of turbines are required to match the output of a single traditional power plant. However, unlike fossil fuels, wind power has zero fuel costs and produces no carbon dioxide or sulfur dioxide during operation, making it a critical tool for reducing our carbon footprint. Building these machines is an exercise in extreme material science. The forces acting on a 100-meter blade are immense. If you made them out of steel, they'd be too heavy to turn. If you made them out of wood, they'd snap. Modern engineers use composite materials, glass-reinforced plastic and carbon fibre. These materials offer an incredible strength-to-weight ratio. They are layered in a vacuum-sealed mould and cured with resin to create a single, incredibly stiff yet flexible component. It's not just about the blades. Structural integrity is key. Onshore, we use massive reinforced concrete gravity bases. Offshore, it gets more complex. Engineers use monopiles, giant steel tubes driven 30 metres into the seabed, or even floating platforms tethered by massive cables, allowing turbines to harvest the high-velocity winds found in deep waters. Maintaining these giants is a feat of logistics. Technicians must often climb hundreds of feet or be lowered from helicopters to perform routine inspections and lubricate moving parts. In offshore environments, specialised vessels are used to reach turbines in heavy seas. Digital monitoring systems now allow engineers to track performance remotely, identifying mechanical stress before a component fails. Before this power reaches our homes, it must be managed efficiently. The electricity generated is typically stepped up to a very high voltage using a transformer. By increasing the voltage, we significantly reduce the current. Since power loss in cables is proportional to the square of the current, this high voltage transmission minimizes the energy wasted as heat, making the entire distribution network far more efficient. Globally, the growth of this technology has been exponential. China currently leads the world in total wind capacity, followed by the United States and Germany. In the United Kingdom, the geography of the British Isles makes it one of the best locations in Europe for offshore wind, with the North Sea hosting some of the world's largest arrays. This global shift is driven by a rapid decrease in the levelized cost of energy, making wind one of the cheapest forms of new electricity generation available today. Where do we go from here? The future is about scale and intelligence. We are seeing the rise of smart turbines equipped with LiDAR, laser-based sensors that see incoming gusts before they hit, allowing the turbine to adjust its pitch in milliseconds. We are also seeing a shift toward direct drive technology. By using permanent magnets, engineers can eliminate the gearbox entirely. This reduces friction, lowers maintenance costs, and makes the turbine much more reliable in harsh offshore environments. But the biggest hurdle remains: intermittency. The wind doesn't always blow when we need tea or light. Because wind is a renewable but non-reliable resource, the next generation of wind farms will likely be paired with massive battery energy storage systems or used to create green hydrogen via electrolysis. This chemical process uses electricity to split water into hydrogen and oxygen, storing the wind's power as a gas to be used weeks or even months later. From a simple wooden sail in a Persian field to a 250-metre-tall marvel of carbon fibre and electromagnetism, our journey with the wind is only just beginning. It is a testament to human ingenuity, our ability to take a force that once frightened us and turn it into the very spark that powers our modern world. The wind is blowing, and for the first time in history, we are truly ready to catch it.